Okay, so what I propose, Maria, if you're okay, it is in order not to be late, we'll start with your presentation, if you're okay.
Of course, of course.
So
Okay.
now the presentation is online as well. So I would like to, first of all, thank all the speakers here today with us and all the audience as well, online audience as well. We will start with the presentation of Maria-Ioanna Pavlopoulou from Sympraxis. The floor is yours, Maria.
Thanks so much. Just give me 1 sec to share my screen again.
Definitely.
See if I understood the test well. I think you should be able to see now, right?
Yeah, Japomon would be perfect.
Okay.
You can go.
Perfect. First of all, thanks a lot, Loic, for your introduction. It's a pleasure to be here today. It's the first time that I'm participating in the Sustainable Places conference. So it's very interesting for me and also for our team to be participating in this session with so many interesting speakers and topics being addressed. So in my presentation, I will be discussing the PEDvolution project, which actually addresses the positive energy districts and how they can, their challenges and how they can contribute to moving towards the energy transition. So very, very briefly, as Loic said previously, I'm just Maria Pavlopoulou from Sympraxis, and we are communication dissemination manager in the PEDvolution consortium. So let's begin. So first of all, taking the first step and how, as regards the motivation for the development of our project, as I'm sure you are all aware, the built environment is very key, and we can even say pivotal to the Europe's energy transition and to moving towards a climate neutral society by 2050, in line with the European goals. Nevertheless, on the other hand, we have an estimated more than 90% of the dwellings which are not fit for this purpose. Therefore, they are not contributing to this transition. Therefore, what the PEDvolution consortium has recognized is actually the need to move away from an isolated solution to improve technologies on an individual buildings level, but rather to move to and implement and develop fully interoperable solutions that reach the neighborhood or the district level. Of course, as you understand, this will be an opportunity to improve energy efficiency, to be able to integrate the local renewables and in a much more efficient and beneficial, let's say, way. So I'm sure as you moving on to the concept of a PED, just very, very, very briefly, I'm sure you are aware of it as well. But as you are aware, the positive energy district in brief is actually an urban area that produces at least as much energy on an annual basis as it's consumed. And actually, this is the definition that we have decided upon within our consortium, because actually it has been defined in multiple ways, and it is an issue that has not yet been established 100%. So taking this as our starting point, let's see what the specific needs of the PEDvolution are, what specific needs it addresses. Actually, in brief, we can say that it addresses the four main bullets. The first one, that it aims to improve the energy efficiency, coupling it with a better integration of the local renewables and excess heat sources within the districts that we are talking about. The second one is that it aims to increase the participation of the citizens and the integration of the consumers and the energy communities in the value chain of the energy system in general. Third, it improves the cross-sectoral integration on energy and non-energy sectors within a PED, within a positive energy district. And finally, it aims to demonstrate and develop fully interoperable solutions that within the whole process of defining and implementation of a PED, so within the planning, the design, the development, and the management of a positive energy district. So moving on in this figure, you can see actually the general concept of PEDvolution and what it aims to achieve. Contrary to to many belief. Actually, the PEDvolution is not an answer in itself. Actually, it is something that needs to be reevaluated, since PEDvolution is actually a positive energy district is always in continuous change due to its interaction with its environment, due to its interaction with its PED genotype and the PED phenotype. In fact, here we have defined the PED genotype as the social, technological, interoperability, and market factors that constitute a PED. And the second one is the PED phenotype, which constitute the observable characteristics of a positive energy district, which actually to see how it interacts actually with its environment. So taking this into consideration, PEDvolution aims to develop 7 solutions, tools, let's say, in other words, which will help us to and managers to design, process, and optimize the PED genotype and phenotype throughout the management of a PED. So here in brief, we can see what are the solutions that we aim to define within the 3-year let's say duration of our project. The first one, we will see them in detail later on, but just briefly here we can say that the 2 of them, the PED design and planning toolset, aim, and the dynamic decision support guideline for PED development, they actually aim to address and to improve the PED genotype, while the 5 remaining others, such as the PED readiness assessment, the PED energy manager, and so on, actually aim to improve and address aspects related to the PED genotype. So in our consortium, once we have developed this solution, we aim to test them, fine-tune them in real pilot sites, 3 of which have already been defined, and three of which will be defined later on in the project, paving the way for the replication, the fine-tuning, and the upscaling and mainstreaming of the solutions. So in this slide, if I can move on to the next one, sorry, you can see some basic facts and figures related to PEDvolution. It is a project that began in the 1st of January 2024 and has ending date on the December 2026. So actually it consists of a 3-phase duration, 3-phase work plan, we can say. The first one consists of an analysis, the second one of a co-development where actually the solutions will be developed, and the third one consists of demonstrating the solutions to the stakeholders and to exploiting the project's results. So the total budget is approximately 5 million euros, and moving on to the next slide, you can see here the PEDvolution partnership. Actually, we are a group of 15 organizations coming from 7 different European countries, which actually try to include the whole, let's say, value chain of a PED. So here we have academic organizations, we have universities, we have SMEs, but we also have public authorities which are contributing to this effort in order to make it inclusive and so on. So here on this slide, we can see the overall project approach in highlights. So here we have, as I previously mentioned, 3 years duration. Each year is focused and on one aspect of the project. So during the first year, now we are in month 9 of the project. We are analyzing the involvement and developing the conceptual design of the project. In the second year, we will be actually developing and co-developing and implementing the solutions. And in the third year, we are basically going to demonstrate, validate, and revise, where appropriate, the developed solutions within the consortium. So moving on to the next slide, you can see what target groups is the project addressing. So who is it for? Who will use its results? Who will benefit from it? Actually, once again, the PEDvolution aims to address all the whole value chain. So here you can see that we have energy service providers, so ESCOs, we have energy prosumers, we have PED investors, we have PED developers and managers, sorry. We also have policymakers, standardization bodies, but also the general public or the citizens of the PED sites. On this slide, you can see briefly the 3 PEDvolution co-developer sites, which have already been defined since the application stage of the project. One of them is, you can see there, from different countries with different geographical and economic statuses. So here we have one in Germany, one in Slovenia, and one in Switzerland. For all 3 sites, it's important to say that actually we have partners within the municipalities that are part of the project, so they are actively involved they will be actively involved in the pilot testing and development of the solutions. And also the other 3 the PEDvolution co-developer sites will be defined in the 2nd year of the project, when we will launch an open call to identify actually more sites which share the characteristics that are sufficient for their pilot testing of the solutions that we will have developed. On these slides, you can see in a bit more detailed the characteristics and the needs, let's say, of each village, of each site. Here, I will not go through them in detail, but of course, this information is also available on our website, but also through the presentation here, which will be shared later on. So in order not to tire you as well, just to say that each PED site has their own characteristics with different size and different status of development. So in this case, the village in Schockenberg-Brunn village in Germany, it is a small village, but with quite a few, 400 households and 9 businesses, and more than 1,000 residents, which is already in operation today. On the contrary, we have the second PEDvolution site, which is actually in Slovenia. It is of approximately the same size, however, it is in the planning stage. So here we also have the contribution of the municipalities and the electricity distributors, which are involved in the development of this process. And thirdly, we have the Winterthur village in Switzerland, which is again a PED site which is in operation. And in this case, it's much, much smaller. So it consists of only 250 residents and 45 apartments and 40 businesses. So moving on to the expected outcomes of the projects once we have developed the solutions, once we have identified the sites where they will be tested. Actually, in response to the aspirations that it has, to the ambition that it has, the PEDvolution project actually aims to increase at the end of once it has been completed and beyond, to increase the availability of the tools that will help the management, the planning, and the design of PEDs across Europe, to help improve the integration of energy and non-energy sectors within a PED site. Thirdly, to improve the integration of PEDs in energy system and improve the integration of PEDs to energy grid robustness. Fourthly, to increase the societal and citizen participation and engagement in the energy communities, which is something that is very, very important and can help significantly into to gaining the feedback from the citizens and the residents that are actually living in these areas. And fifth and lastly, to increase participation of consumers and energy communities in the value chain overall. So here we have again the list of the solutions that will be developed, and briefly we can take a look at what each one of them aims to achieve. So first of all, we have the PED design and planning tool, which actually is envisioned to be a digital twin planning tool that will aim to help developers and managers to accelerate the district development pathways and achieve, let's say, be able to facilitate them in making informed decisions about the evolution of a PED site. The second one, which is actually being coordinated and the development is led by the University of Zurich, is the PED Development Readiness Assessment, which actually It's envisioned like a systematic process of monitoring and determining the performance of a PED in relation to some defined essential characteristics that each PED has to have. Thirdly, we have the dynamic decision support guidelines for PED development, which in this case is led by the National Technical University of Norway. And here, this solution actually entails the development of specific targeted guidelines and efficient workflow of PED development decisions, which will actually help, which will actually be able to help the users to make the correct choices as regards the technologies and strategies with respect to the urban planning that they are developing. Then we have the PED Energy Manager, which is our fourth result, our fourth output, which in this case is led by our Slovenian partner, the Offset Energy company. So in this case, this tool entails a multi-level tool for efficient management of energy processes within a specific PED, and it aims to control energy processes both within residential and non-residential environments.
Maria,
Yes.
Just to say, you have still 4 minutes left.
Yes, I'm nearly done.
Yeah, it was just to say, sorry.
No worries. Okay, so let's move on quickly then to the next solution. So here we have the data exchange platform, our integration and interoperability platform, which actually is developed by our Greek partner Inlecom Telecom. And the aim of this tool is it will compromise the digital backbone of the project, since its goal is to unify the energy node information flows and be able to facilitate this process as regards a node for trustworthy data exchange. So moving on to our sixth solution, we will also be developing a PED business model, which, if I'm not mistaken, will be also developed by Smart Innovation Norway. So this is our second Norwegian partner that we have in the consortium. And this tool will aim to be a set of building blocks which will have proven to have community-based business solutions. And it will be able to show PEDs how to adopt business patterns to the local context, which is something that is very, very important because, as you're already aware, positive energy districts, each one of them has its own characteristics. They have some similarities, of course, but they are also unique in their let's say, environment, in the people, in their residents, and so on. They have their own characteristics as well. And finally, we will be capturing the social aspect and developing a social innovation tool. And this tool will aim to contribute to a long-lasting adoption of the planned or existing energy innovation in a PED site. So if I'm not mistaken, this is it. Thank you very much for your attention, and I'm here for any questions or comments you may have.
Ευχαριστώ, Maria.
Παρακαλώ. Should I?
I know, yeah, I know it's always complicated, hard exercise to do it online in 20 minutes. So many thanks to the time. I'm forced to respect the rules and give the same time inside the conference. So thank you very much for that.
I understand. Thanks a lot.
So we will go to the next presentation. Should be now Florencia.
Yeah, here I am.
Good afternoon, Florencia.
Good afternoon.
Okay, at the beginning I showed the way to share your screen. So at the bottom of the screen you should see share. Select all screen.
Okay.
And if you have opened your PowerPoint, you should be able to share the PowerPoint with us.
Okay. Can you see the PowerPoint?
Okay, you can now diapo mode. Yeah, that's good.
Okay.
Yeah, perfect. So you have 20 minutes, and I will just give a signal 5 minutes before we end.
Okay, thank you. Good afternoon. I'm Florencia de Maio from Rina Consulting. Today I will present the our work building resilience through cascading impact analysis, an European perspective that is led by Rina and Norsar, our Norwegian partners. Rina is a company that deal with different teams. We have different competencies from the civil, structural, and hydraulic competencies, but also the geology and geotechnical design. But today we will consider a project that lead with the climate change risk assessment and the risk and resilience analysis. In particular, today I will talk about the MEDIATE project, multi-hazard and risk-informed system for enhanced local and regional disaster risk management. In general, when we make a risk assessment, the main challenges are that different phases of hazard and risk are often addressed separately, that the risks are not performed from a multidisciplinary perspective, and in general, in risk assessment, compounding and cascading effects are not considered. We try to solve all this problem with all the partners of the MEDIATE project. We are 18 partners from all Europe, from Italy, Norsar, UCL, Rina, University of Padilla, U-Centre. The solution that we found during this project that is not finished yet. So we are still delivering some results and documents. However, in general, the aim of the project is to consider multi-hazard risk assessment scenarios, to consider the preferences of the decision makers, the context, and create risk-informed decisions. In particular, Rina, the main task of Rina regards the cascading impact assessment. To assess all these analyses, these are the main steps that we follow, starting from the definition of the key concept regarding the cascading impact, the selection of the main sectors and of the main hazards, so the context selection. Then, thanks to the literature review, we define the methods to assess the cascading impact, and all the analysis is based on a machine learning algorithm. So we selected different algorithms that can represent our analysis, and finally we validated the analysis throughout different case studies. Regarding the definitions, in general, we consider only the direct impact, that are the impacts that arise from disruption of critical elements causing an immediate effect on society, while cascading impact propagate throughout the infrastructures. The propagation is due to different dependencies and interdependencies between the sectors. In particular, as REAC stated, the dependencies is between the sector A and sector B is a one-way linkage, while if both the sectors are influencing each other, we have an interdependency. And as Rinaldi explained different studies, we can have a different type of interdependencies. The geographical, that is that happens when local events can create a change in the in other infrastructures thanks to the spatial proximity, the physical dependencies when the material output of a sector can affect another sector, and logical when we have we don't have a geographic connection, but we have a link, a dependency on the state of the different sectors, and the cyber interdependency or dependencies when an infrastructure is dependent on the information transmitted throughout the information infrastructure. In particular, the analysis of the logical and geographical sector. As I said before, the methodology developed for the assessing of the cascading impact is grounded in the machine learning. The algorithm has been chosen between different type of algorithm that we can use for the machine learning. In particular, the multi-regression supervised method. This is the workflow of the analysis. We started with a database. The database is the the first part to assess analysis with the machine learning. Since the machine has to learn from something, we have to find the right database of historical data. So once we define the database, we can give to the machine all the data to learn and to find a correlation between the elements of our database. In this case, the database was the Inventar that follows all the Sendai recommendations and that has a clear definition of all the historical database. As you know, we have different also MDAT or a lot of historical databases, but sometimes there is a lack of information. So starting from the direct impact that we analyzed with the machine learning, we define the impacted sectors for the different case studies in Europe, and then we calculated the cascading impact considering the logical and geographical sector interdependencies. So considering the database, the machine learning requires a constantly evolving database of past events to be for the training and the testing. We compared different databases, as I said before. This inventory is being selected because the events are geolocated. It provides the damage of a large set of sectors. And the collection of historical disaster losses are provided in a systematic way. This was the main challenge of the machine learning approach for the cascading impact, but in general, that is the data scarcity. Given the database, we considered the 80% of the database for the training of the machine and 20% for the test of the machine. And then we, thanks to all the algorithms behind the analysis, we considered the indirect impact of all the sectors that were most relevant for each case study. So starting from the direct impacted sector, we defined different propagation of the impact, considering the most important critical sectors. This is an example of for the case study of Oslo, where we focused on the house damage, the education sector, health sector, agriculture, water supply, transportation, communication, and power and energy. Thanks to the machine learning algorithm, we noticed that power and energy and transportation were the direct impacted sectors, and then we propagated the impact to the other sectors. So we can observe that power and energy and transportation, that are also critical infrastructure, create a direct impact in their sector, but also in a lot of other sectors like the education, the water supply network, transportation, and health sector. Here we summarize the results for the different case studies. In the case of Mediate, that is the project, the European project, we have 4 case studies: Oslo, Essex, Nice, and Mulaping. Each case study has a different other context, different main assets. So we tried, as we made in general in the European project, we tried to replicate different contexts, and we can see that considering different hazards and also different assets, in general, the sector that propagates more impact are the transportation and the power and energy sectors. And we can also from the last event we have a sort of validation also of this result. So just to of course the project is also is not finished, so we are making a lot of other analysis. This is the first step of of the task of the project and of the task of Rina. Regarding the future development, we can apply the same methodology, considering also other sectors and considering a variety also of societal sectors, and methodology is appropriate to a large critical infrastructures, since it is not linked to the asset, but to mainly to the database. That is very important. One point that I want to stress is the importance of the historical event data, so the availability of data, because if we don't have historical data, we can train the machine learning methodology. What is very important is the involvement of stakeholders to identify the relevant hazard and also the relevant assets for each case study. And each individual phase can be refined, of course, with more detailed analysis, also given more accurate data. I think that I finished. Thank you for your attention. If you need more information or if you have questions, I'm here. I think that I am on time.
Yeah, definitely on time. Thank you very much. Grazie mille, Florencia. Thank you very much for your presentation. So now I will give the floor to the following presentation, that is Rafael.
I'm sorry, my screen, wait.
So, yeah, perfect.
Okay, can you see?
Yeah, but if you can put diapositive mode at the bottom and then, yeah, okay, perfect.
Okay. Good afternoon, everyone. My name is Rafael Camarero Rodriguez. I'm a technical researcher in CIRCE, and today I will present our work on in one of the tasks of the effort project, which name is Grid Verification and Monitoring Layer by Blockchain Technology. Well, first, I will start giving an introduction of what CIRCE is, what is our objective, which activity lines do we have. Then we will go ahead with the project, which is the consortium, what is the target and the demo sites. After that, I will provide a brief description of what blockchain is, its foundations, the types, and the possible usage of this technology. Then I will present our design solution, the infrastructure we have used, and the data model. And then I will talk about the next steps and how we will use it. Well, first we will talk about what is CIRCE. CIRCE is a technology center which was founded in 1993, and our main focus is to provide innovative solutions for a sustainable development. We have participated in 105 European projects and 29 coordinated by us. Also, we have a high success rate, around 50%, in the proposals that are completely elaborated by CIRCE. Also, we are a 10% self-funding center, and we have shared more than 100 million euros between our partners in the European project that CIRCE coordinates. We have 6 activity lines: renewable energy, future electric grids, smart mobility, industry 4.0, energy efficiency, and circular economy and sustainability. Now I will provide a brief description of what effort is. Effort is an Horizon Europe project with a total budget of around 9,300,000 euros. It's coordinated by CIRCE and involves a total of 23 partners from different countries such as Italy, Netherlands, Greece, Norway. And the main goal of the effort project is to transform the current electrical and power and energy system into a more resilient, reliable, and secure system all over its value chain. The blockchain technology helps to improve all of those points. We'll see later how does it. We have a total of 4 demo sites. The first one is in Escúzar, Spain, where we will test blockchain, cybersecurity, and IoT developments. The second one is in Delft, Netherlands, where we will test cascading effects and grid resilience. The third one is in Sarentino Valley, Italy, where we will test flexibility and islanding operations. And the last one is in Ilzy, Ukraine, where we will test digitalization and secure design. Now, when the context is clear, we can start to talk about what has brought us here, the blockchain. First, I will talk about the foundations, the different types of blockchain, and its usage. First of all, blockchain is a technology that is created to share data across different machines, and the foundations are the following. The first one is distribute. The data is not held in just one machine, it's shared across all the machines that belong to the network. Second one is immutability. Once a record is created, it cannot be modified or deleted. It will be stored permanently to ensure data integrity. Third one is traceability. Since every transaction is transparently recorded and can be checked by anyone on the network, any transaction can be easily traced back to its origin. And fourth one is secure. The usage of cryptographic techniques to ensure the identification of every peer or machine along with data encryption keep the data transmission and storage in a protected way. There are different types of blockchains. Everyone has its own usage. We can identify 4 types: public, private, hybrid, and consortium. The main difference between them is how they handle the permissions of the peer to join into the network and to read and write transactions. In public ones, everyone can join and create transactions. The advantage of this type of networks are the independence, the transparency, and the trust. Meanwhile, the disadvantage are the performance, the scalability, and the security. And it's mainly used for cryptocurrencies and document validation. In private ones, on the other hand, are those networks that are centralized by a single organization. This organization is the only one who is allowed to select to choose who belongs to the network and which transactions are valid. The main advantage of this implementation is the control of the access and the performance, whereas the disadvantage are the trust and the auditability, and is normally used on supply chains and asset ownership. In other hand, we have hybrid ones, which in the same network we have both public and private. So some parts of the network remain public and some parts remain private. It has the advantage of the access control, the performance, and the scalability, and the disadvantage of the transparency and the upgrading. It can be used on, for example, medical records where some data must be protected, and in real estate. The last one is the consortium networks. Consortium is one type of network that is private, but the decisions are not just made in one entity. Instead of that, there is a consortium of entities which decides who can join to the network and who can read or write transactions. It has numerous advantages, but the main one are the access control, the scalability, and the security. Meanwhile, the transparency is only its advantage. These kind of networks are very useful in different areas that need cooperation between different companies, for example, banking, research, and supply chains. And this is the type we have choose for our development. Now we will go on with our proposed solution. We are leveraging blockchain technology to facilitate the exchange of essential information among 3 groups of organizations: maintenance, owners, and manufacturers, to ensure the optimal functionality of the components that make up the electrical grid. This includes managing the supply chains of various components such as wind turbines, IoT device, solar panels, and power plants. The blockchain will be used to store and share critical data, including manufacturing dates, maintenance history, and the specific component that comprise these elements, among other crucial details. Effective management and collaboration among the 3 companies are essential for this task. And if you look at the left of the slide, we can see that maintenance wants to share installation, repayments, removals, and upgrades. On the other hand, owners want to share the cyber attacks, the contractual documents, and the component states. Meanwhile, manufacturers share technical specification and documentation about their components. This is the diagram of the network we have designed. It contains several different components. Firstly, we have the TLSCA. It's in green color, which is an unique component, and its purpose is by using public key infrastructure to cipher the communication between network components, allowing a secure way of communication between them. Secondly, we have the organizations. Organizations are a group of related peers. In this case, as said before, we have three groups of organizations: owner, maintenance, and manufacturers. Then we have the Organizational Certification Authority, which is a component that issues organizational membership, and it needs at least one per organization. It defines which peer belong to the organization and can create or revoke the peer certificates. Then we have channels. Channel is a pathway of private communication that allows a specific set of organizations, those who have joined into the channel, to share data in a private way. If you look at the diagram, you can see we have three of them. The first one is system channel, which is a must-have channel in this type of implementations. It is the first channel created, and it defines the ordering service, and we will talk later about it. The channel number one is focused on controlling the supply chain of different components that shape the network, and the purpose of the channel number two is to offer stability to the network. On one hand, the transmission system operators monitor this channel to know the consumption and production of energy. This channel is out of the scope of this presentation, so I won't go deeper. The next component is the ledger. A ledger is a record of all the transactions that have been generated by the peers in a specific channel. It keeps all the data and the changes that were made since the creation of the channel. Next, we have the order, which is a specific type of peer that is responsible for keeping the ledger integrity by ordering the transactions and validating them. In other types of blockchain, for example, on Bitcoin or Ethereum, that rely in probabilistic consensus algorithm, which are vulnerable to divergent ledger, also known as ledger fork. Because of that, orders were created relying on deterministic consensus algorithm that guarantee that any block validation will be final and correct, making it impossible to have ledger forks. After that, we have the peers, which purpose is to create transactions and keep a copy of the ledger. Every organization can have as many peers as they want, and it's possible to stabilize roles. For example, an administrator will be able to approve and join the organization into a channel. Meanwhile, writers will be able to only create new transactions. And the last component is the smart contracts, which are the definition of the executable logics that generate new transactions. The smart contracts can be automated to perform some action autonomously. For example, on the channel 2, a smart contract will be activated when a deviation of the network is detected and perform actions such as connecting or disconnecting energy sources to correct the deviation. But all these networks have been created to be flexible. So this is just our initial design, but as you can see, we have two figures, network administrator and the end user. The network administrator is responsible of the network design under his organization and can create new peers, create new order channels, etc. On other hand, the end user, which will be, for example, the operators, will have a different interface, and it will allow them to interact with the smart contract that has been developed. Well, this is the data model we have proposed for our channel. Since blockchain runs over non-SQL database, it's offered the normalized and fast-read database, where event is the main class and the rest are embedded into it. We can have two types of events, attacks and maintenance. Attacks will cover all the disturbance produced by external situations, such as cyber attacks, connection failures, electrical outage. Meanwhile, maintenance will cover all the life cycle of a component, from the installation through the periodic maintenance, replacement, till the removal of that component. Every event can be produced in as minimum in one component. And the class component, as we can see, it's auto-reference. We have designed that way to be able to establish hierarchical representation, meaning that if we see if we are looking at information of a component, we will be able to represent in a plot or similar tree, or in a tree or similar plots, the subcomponents and the components and the upper components of it. This is very useful since, for example, if you are looking for cyber attacks that an EV charger has received, you will be also interested on see what cyber attacks the power unit has received. Also, you could be able to see a full report of what maintenance has been done in all the subcomponents, and this will also help the navigation between components to be faster and easier. In the component class, there is a field called documents. This field will allow to exchange specific documents for that component. For example, contractual documents, and every component must have a model. This class will be filled by manufacturers and contains technical information about the component, along with document. And this field will allow to share a kind of documents. For example, manufacturers can share electrical diagrams of component papers or even 3D models of them. And the last class we have is entity. This class is referencing various other classes such as operator. And this one will be, for example, the company, the operator who has realized the maintenance works for. And also in component, where we have it referenced 2 times. The first one is the owner who owns the component, and the last one is the supplier of that component. And now we will go ahead with the next step. Our proposed usage, which we are already developing, is an integration between augmented reality glasses, which will retrieve information of the blockchain, and through object recognition will show the related information of that component. And these glasses are augmented reality ones, which means that it doesn't blur or interference with the vision, which wouldn't be acceptable on this context, since the operators needs to have a clear vision, and it also allow haptic iterations, meaning that the operator wouldn't need to use a remote or to interact with the blockchain.
Rafael, just a word to say, 5 minutes left.
Okay. Here we have 2 examples of it, of how it will look like. The first one shows a CIRCE ordinary electrical vehicle charger, and in the interface we can see an electrical diagram of a subcomponent, and also a table with the information of the events. And on the other hand, in the second image, we can see one of our inductive electrical vehicle charger, and also we can see a 3D model of a power unit, which is a subcomponent of the charger. You can perform some operation with it, such as rotation, and select other subcomponents, zoom, etc. This will help the operators on component verification. And in conclusion, blockchain can help to transform your systems into a more resilient, since you can lose as many machines as you want. Meanwhile, the consensus is still possible to achieve. More reliable, since you can track any change on the data and know exactly the origin of it. And more secure, since it uses numerous layers of security, such as public key infrastructure and IPsans. With the usage we are giving to the blockchain, we are also contributing to transform the electrical grid into a more sustainable system, since blockchain helps to fix the deviation of the network and the detection of weak points or imbalance in the infrastructure. And this is all from my side. It was a pleasure to be here, and thank you all for your assistance.
Thank you very much. Muchas gracias, Rafael de CIRCE, for your presentation and for the time also, as I said previously. Thank you very much for that. I will give now the floor to Anna Pinnarelli from University of Calabria.
Okay. Good afternoon, everyone.
Good afternoon.
Try to share my screen.
So on the bottom, you will have
yes.
Share. Okay. Yeah.
Yeah.
Did you open the PowerPoint?
Okay. Yes.
Okay, but
do you see my vision?
You can put it in diapositive mode. Okay, that's nice.
Okay, thank you very much. Okay, good. Thank you very much for the invitation or for this event. So I'm Anna Pinnarelli, Associate Professor at the Department of Mechanical Energy and Management Engineering of the University of Calabria. My expertise in smart grid, in particular for the power electronic converter. And today I wanted to present some results of our research activity developed in several European projects, in particular the last project Balance Plus that finished in March of this year, and other national projects that are in progress in this year and next year. My presentation of today is towards the energy transition, the role of the renewable energy sources, the energy storage system, and the hydrogen. So a brief summary of my presentation, an introduction to give a framework of the context in which my research activity is developed, in particular in terms of energy for to support the energy transition, so the deep decarbonization, and so to target the goal of 2050. In particular, we have analyzed the problem in terms of integration of renewable energy sources, and we have considered the key role of the energy source system and the hydrogen as an opportunity. In particular, it is necessary to understand what is the energy transition. The energy transition implies an increase of the renewable energy source penetration, the increase of energy efficiency, and so contemporary the increased use of electricity to meet the needs traditionally required for the direct use of fossil fuels. So the energy transition is a transition toward a zero-emission energy system that imply a deep decarbonization, so the natural climate for the of 2050 in terms of environmental, energy, and climate targets. So it is necessary to change the scenario that can be all electric scenario, and so this imply a deep increase of RES. But to support and I think it's better to say to accelerate the energy transition, it is necessary to consider and so exploit new flexible resources to ensure the necessary levels of system stability, safety, and resilience. And so it is necessary to implement a new paradigms in terms of produce, consume, and particularly share energy. At this scope, it's necessary to have to have clear the target of 2050. Based on two key pillars, diversifying gas supply and reducing faster the use of fossil fuels. But not only in industrial sector, but also in residential, in general, in all energy sector. And so, according to the latest IPCC report, it is much cheaper to cut emission immediately using renewable energy sources instead of coal, gas, and oil, and then remove them later. So it is necessary to realize a new model to better integrate this increase of renewable energy sources with some to guarantee the necessary security and reliability of the power system. In particular, in this context, the increase of renewable energy sources is considered a problem for the power system, and so it is due to the uncontrolled controllability of the RES, the unpredictability of the generation capacity, and no matching between the generation profile and load profile. So this implies balance the system, congestion on the network, some problems in terms of frequency regulation, and so on. So it is necessary to implement in our network new solution, not only in terms of technological solution, but also in terms of smart digital solution. The people solution that can be integrated to support this increase of renewable energy sources are mainly smart meter to monitor the consume and the production necessary to coordinate to control this, macro nanogrids to integrate several resources energy as generation and storage system, and so on. Smart storage system that it is necessary to increase the programmability of management units to manage new flexibility resources, and so to target the objective, the whole serve the stability, the reliability, and the resilience of the power system. Integrate also smart appliance IoT device to communicate and control, especially at the local level of the end user. And it is necessary also a smart interoperable platforms to coordinate these distributed resources. Only using the principal smart digital and technological solution can guarantee a balanced system, considering the high number of renewable energy sources plants that integrate in electrical network, in existing electrical network. Naturally, the energy storage is the key element that allow maximizing the efficiency of an energy system, because due to the technical characteristic of this storage system in terms of speed of answer, they can provide both power intensive to network reliability, but also energy intensive services to solve some network congestion, and for to provide the services so load shifting, pack shaving, peak shaving, peak sharing in terms of frequency regulation, and so on. In particular, we highlighted the use of not one central storage system, but in a balanced project, we have considered the model of distributed energy storage system. So at the local level of the end user, a single smart storage system is integrated, has flexibility resources at local level, but when aggregated, we can consider a single distributed energy storage system in terms of this approach. And so considering an high power storage system at the central level, but distributed at the local level. So for this, it is necessary to consider a new model in terms of technological solution at the local level, at the end user level. In particular, we have considered and modeled and also implemented in terms of test facility a new model of hybrid energy system, in which we have a common DC bus, as illustrated in the picture. At this DC bus common DC bus, we have integrated several can have integrated interfaces several resources in terms of generation, for example, PV generation, wind, steam engine, biofuel engine, and so on, but also in terms of storage system, can be in supercapacitor, conventional battery, fuel cell, or electrical vehicles, because an electrical vehicle can be considered as a storage system on 4 wheels, and interfaced to the network by an ICDC converter. This solution must be modular and flexible, so I can change configuration time by time, integrated or not integrated, and so not consider one of these general plant or storage system. And we have implemented several test facility in our campus. In this presentation, I illustrate only the two principal test facility. In particular, we have in this case a integrated DC to DC nanogrid, one in that integrates a conventional battery and a hydrogen storage system, and other DC in which we have a PV plant, a biodiesel biofuel engine, and a controllable load. Another configuration of DC nanogrid is this, which we have a supercapacitor and a VP plant. And all these test facilities are distributed in several laboratories of our campus, and they can communicate by a platform, indeed, for each test facility is installed a gateway for the communication. In this way, this test facility can have some information each other, and so we can coordinate by the platform, in particular from using the optimization algorithms that have been implemented on this platform to coordinate these test facility distributed in our campus in a coordinated way. In particular, we have also other DC-AC hybrid nanogrid, in which we have 3 nanogrid that have integrated on the same AC bus bar. Implemented hybrid energy system with an higher size and with several distributed storage system and also PV plant. This is the hardware component are installed in a residential center of our campus. So in this way, with this modular configuration, we can adopt a bottom-up approach, and so we can realize it and so implement islanded microgrid with several number of end users that can be increased time by time, and we can consider that we can integrate not only in terms of DC bus, but also in terms of AC bus. It is necessary to implement an opportune control strategy at the local level for each nanogrid. In particular, we have implemented a hierarchical control architecture with these layers that I've illustrated in this picture: the system control layer, the application control layer, the converter control layer, switching control layer, and hardware control layer. So we have a top-down approach. The system control layer is higher level that receive the power reactive and active active power profile from platform, or for example from the DSO or TSO in terms of distribution or transmission network operator, and these references are translated in reference for the control for each converter that interface each sources to the DC bus, and so to control each converter to in a coordinated manner at the local level. For this,
just one word to say, 5 minutes left.
Oh, yes. For this, we have implemented a state machine, in particular the DC bus signal control. This is an example of control of grid converter. For more detail, we have this publication. The hydrogen, we have consider also the hydrogen, because the hydrogen can be an opportunity to accelerate the decarbonization of our energy system, because the hydrogen can be used for the transport, for the network balancing, for the industrial procurement, and also for commercial use. Indeed, we can adopt the hydrogen for 3 ways in terms of integration and operation. In particular, we have considered all three scenario: power to gas, power to power, and power to grid. Power to gas to store energy over long periods, and distributed this energy this energy stored on using the gas network. Power to power is the surplus of the renewable energy source production can be stored long term and used using, in this case, the power network. Power to grid, the hydrogen can be used also to provide the service, ancillary services to support the network. Actually, it is considered the hydrogen as green hydrogen, and so produced by the surplus of electricity generation from local renewable sources. For this, we have considered a multi-carrier energy and cross-sectoral framework, as illustrated in this picture. So we have considered the several sectors in terms of transport, in terms of industrial, in terms of residential, and particularly we have considered that each building in several sectors has an active building. So in this way, each building can exchange energy with the other buildings independently from the sector. And for this, we have implemented a model for each component of hydrogen system, for the electrolyzer, for the storage, compressor, and for the fuel cell. And we have adapted the DC bus signal previously implemented, considering also these new flexibility resources as in terms of hydrogen. And also for this, we have implemented a state machine. And also we have implemented the optimization model, in particular a mixed integer linear programming model for the sizing of an hybrid energy system integrated and conventional battery, but also the hydrogen system. And also this model can be used for the HAID management. And we are implementing and developing also a digital twin suite platform for microgrid that integrates hydrogen. So services to complete the platform for the management of these distributed energy resources, and not only in terms of monitoring, fault detection, diagnosis, for the forecasting, for the predictive control optimization, for the flexibility management, and for the mission verification. So I conclude. Thanks for your attention.
Thank you very much.
Okay.
Sorry about that.
Don't worry.
Mi scusi, sono costretto dalle regole per la conferenza.
It's normal.
Sorry about that. Very nice presentation, and it's always hard to be the one to control the time, but I have to. So thank you very much again. And now we will go, I think, so Colin, I saw you could come. Thank you very much for that. You were forecasting the first. I saw you had the trouble with the time zone. No problem. It can happen. Don't worry about that. So maybe we can continue with your presentation.
Sorry, can I do it now?
You were forecast at the end. That's why wrongly I
Yes.
was wondering. But you have to leave earlier.
If possible.
Colin, is it okay for you?
If you'd like to go next, please do. I'm happy to.
Okay.
Thank you so much.
Thank you very much.
Okay, I will.
So at the bottom, you have share.
Yes.
Share complete screen.
Entire screen.
Entire screen, yeah.
This one. Share. Then.
Yeah, definitely.
Is this okay?
Yeah, it is open. We can see diapositive mode, and then it's goes. So 20-minute maximum as the others. Thank you very much.
Okay. How do I swap? Great. Now it's best.
That's good.
Okay. Thank you. Hello, everyone. We're not so many people here, I see, but it's very nice to meet all the speakers. And so I'm the coordinator of a CIRCE project, which is on cost-effective and replicable renewable energy integrated electrified heating and cooling systems for improved energy efficiency and demand response. I'm an associate professor at DTU in Denmark, and I'm also coordinating IEA EBC Annex 82 and 96 on grid integrated control of buildings. So if you have projects and colleagues who work on energy demand flexibility in buildings, please reach out to me. We have a platform for across the entire globe with people from different continents to work on this common research topic. And at the same time, I'm also a board member of Horizon Europe Build for People partnership. So what is CIRCE? CIRCE is about electrification of thermal demand in buildings, including both heating and cooling systems. And we in CIRCE would like to develop integrated and scalable methodology that can integrate more renewable energy in the decarbonization of heating and cooling systems and the smartification of HVAC systems. We here using and developing different types of heat pump systems in different demonstration sites that I will tell you more about later on. And so we have 6 focus areas. First, we try to reduce the thermal energy demand of buildings by retrofitting and renovation. And then we increase the efficiency of the technologies, heat pump, HVAC systems. Then we deploy energy flexibility of those systems to enhance the stability of the grid. And also to increase on-site renewable energy integration. At the same time, during design and operational phase, we try to minimize the cost and consider the life cycle environmental impact. So in the end, we are developing this method and solutions not only for the demonstration side. We aim to replicate those solutions in Europe. So we have dedicated team of people work on replication and how to support decision making. So at a glance, we are 26 partners. It's a larger project with 6 pilot sites and 48 months. It started January this year. We have received funding from a European Commission for a bit more than 12 million euro. And with the timeline, it's a 4-year project. And this year, we focused on design of the renovation, retrofitting system, and there's one new construction project. So we focus on the design of this new construction. Then the local partner are working hard on getting permissions and tender in place. In this phase, the RTO are supporting with the LCA analysis. The pilot owner are working on mapping and survey of demonstration site. And some demonstration sites are working very fast. They have already started to even implement some solutions. Next year, we will be focused on installation, construction, and develop algorithms that can be used in the operational phase. And starting from next year, we will also start to collect operational data, which we will use in the years to come. In the third year, the focus will be measurement testing of different algorithms and the solutions. The last year is more on validation, implementation, and upscaling of the SAIDS methodology and solutions to potentially other countries. And the consortium, we are 26 partners from 8 states, including one in Ukraine as associated member states. And such a large consortium consists of 5 local value chains in 5 demonstration countries. So each value chain consists of the value chain consists of different type of stakeholders. For example, we have municipalities, cities, and policy bodies who play a crucial role in the development of upscaling activity and also decision-making support tools. We have developers, housing association, and building owners. They are mostly pilot providers and owners. They lead the demonstration activities. They are really active and crucial partner. And we also have designers, architects and consultants who play a very important role in the design phase and also dissemination communication and innovation management. Knowledge providers, we have a few RTOs that support the local technology development and demonstration, especially on smartification of heat pump systems, optimum design, optimum optimization, operation of the systems. And technology providers, they are crucial to provide critical elements. For example, Daikin is a provider of a heat pump to several demonstration sites free of charge. And we have AI Energy SME who has a very smart solution to plan PV for individual building based on the roof area and the roof angle, for example. Energy companies are crucial. They are high on the value chain. We develop a solution, harvest energy flexibility to provide to the energy companies and for them to use in their energy flexibility service and enhances the stability of the grid. So the next one about the 6 pilot sites. In Denmark, Belgium. In Belgium, we have 2 pilot sites. So within the 4 year of the project, we're going to replicate the solution from Belgium site 1 to Belgium site 2. In Slovenia, we have a pilot site, Hungary and Greece. So these are from different climate zone and with a very different type of buildings and different background of use of those systems. We also have a partner from France, Italy, and Ukraine, and play an important role in communication dissemination, upscaling. Especially in Ukraine, we are making a plan for the specific case there. So the team, we had our second consortium meeting earlier this month, very successful, and everyone was very motivated by the progress we have made in the first year. And as a coordinator, I'm very proud to be the coordinator of this project. I think many of the participants share the same feeling of being proud of such a good team, which is a good feeling. So SID's workflow, we have the 5 pilot countries with 6 pilot sites. And in all these sites, we focus on 6 areas. Starting from design, we design, no matter it's a renovation or new construction, we design the best systems for improved energy efficiency. Then we also focus on using data-driven and sensor-driven method for optimum operation. So data platform, IoT devices are crucial. That's another focus area. Then during the operational phase, we'll optimize the energy efficiency and the flexibility of those systems. Then the fifth, then the fourth one is,
can
yes?
you hear us?
Yes. We can hear you. Is there any question?
We don't hear you anymore.
Oh, that's strange.
Somebody can.
I'm hearing here.
Can you hear me?
I can hear you.
Yeah. Okay. If people in the room can hear me, I can continue. Okay, shall I continue?
Yeah, you can carry on.
Okay, thank you. Yes. Okay, then we move on to a very critical area that's deploying energy flexibility, where we have a real-life demonstration in 2 of the pilot sites that I'm going to highlight later. Then dedicated group working on replication strategies, business model exploitation, another one very critical decision-making support framework for the replication. So next, move on to pilots. We have pilots in 5 countries have very different characteristics. For example, in the Belgian side, the 2 pilots are both historical houses, and they are a cluster of houses with 20 households. Here we design integrated renewable energy integrated heat pump system to provide kind of district heating to those cluster of houses, and the optimum design and optimization of operation, including using MPC, is part of this demonstration site. And critically, the replication from site 1 to site 2 will happen during the project. So this will show the experience and the solution and to other historical cities in Europe how to decarbonize heating and cooling systems for heritage homes. The Hungarian pilot is a very interesting and unique one. It's a very old building with a very poor condition, I can see. Those heating system is a gas burner inside the individual room. That is very unhealthy and definitely critical for decarbonization mission. So here, regarding this unique situation, we are using a VRV heat pump for individual room and using the existing opening that is open for the gas burner to install the pipes for the heat pump system. So it's reduce disturbance to the residents there. It's non-intrusive renovation. Here we also consider using energy storage and the PV and the rooftop. Another highlight is innovative material for external wall thermal storage that's developed by Saint-Gobain. And the Greek pilot site is campus building dormitory in the north of Greece, where they have both heating and cooling demand. So the uniqueness of this site is that on the site nearby, there is a large solar thermal field and existing geothermal system. So here we can use hybrid multi-source heat pump for the heating and cooling services for this dormitory. And in the dormitory, we're going to also have a lot of IoT sensors installed to implement data-driven AI solutions for control the heat pump system and the maintenance, improve thermal comfort, and also to forecast the energy flexibility of this building and the system. So the Danish pilot site is the only new building which is not built yet. We have designed this building, and LCA analysis has been done. Then this building this construction is started, and within the next year it will be built. So in this building we have second life battery, an EV charger, chiller, ventilation system, and the PV. Here we are going to manage the electricity production consumption and minimize electricity cost. In this case, the building can have a dynamic electricity price accessible. So we're going to control the HVAC system using the real-time dynamic price to deploy the energy flexibility here. And the real-time dynamic electricity price is available to end users in Denmark. It's about 60% of end customers choose to use real-time dynamic electricity price. The last pilot site is in Slovenia. It's very interesting. There are 5 petrol stations. They're going to renovate and retrofit the HVAC system there to aid the PV and integrate those systems and control them to include them into existing flexibility providing devices, for example, other large storage system, other buildings, and then such in this way, this 5 demonstration site will be able to participate in the flexibility market for both TSO and DSO. So these above are the pilot site, and move on. The contact information. I'm the project coordinator, and we have wonderful colleague from R2M responsible for the communication and dissemination. So if you have any questions, send email to me or to our colleagues in R2M. Thank you a lot.
Thank you, Rongling, and thank you for your presentation. Thank you also for R2M. So we are pleased to be with you. Anaïs is basically here with me as well, and Suzy from our communication team. They helped me. They supported me with the small technical issue I just got. Sorry about that. Thank you again for the presentation.
Good, you are back. Thank you.
So now we go to the last presentation from Colin.
In this talk, I'm going to be introducing a Horizon Europe project called PV for Plants, in which we're going to be developing a new agri-PV system. And I'll be explaining the benefits for doing this. So just to get everyone up to speed before I start, agri-PV is a way of optimizing solar energy use by crops and using land for renewable energy at the same time. So solar panels are deployed in the same land areas as crop production. And we have multiple goals in our project, but really what we're trying to do is use the synergy of agri-PV to both improve crop production and also generate renewable energy at the same time. We're going to be involving end users in this. We're using innovative ways of prototyping our methods in the lab. We're going to be deploying test rigs in the field, which have this innovative control operation. And we're going to be thinking about the life cycle of the project at all stages. So we're thinking about circular economy and producing the panels and their full lifetime. And then we're thinking about how our system will deploy into various climatic conditions, and then think about how to finance this kind of technology going into the future. So we have 3 test sites. The first in Bursa in Turkey is being constructed currently. And here we're going to be growing tomato and green peas. In Avila in Spain, it's a slightly different setup. We're going to be growing microalgae as a way of recovering nutrients from animal agricultural system. And then in Denmark, we're going to be putting our system into a market garden where they grow various vegetables for our local markets. We have a range of partners covering the continent from Turkey, Greece, the UK, from Spain, and all of us are working towards this final outcomes. Italy as well. Okay, so just starting off with the user acceptability, initial work suggests that stakeholders are all right with this plan. Our work across all three regions suggests that acceptability is within the acceptable range. And the project has three particular innovations, technological innovations, that are quite important. So the first of these is that the solar panels themselves won't cover the whole land area. They'll be embedded within a glass in which nanoparticles are embedded. And these nanoparticles absorb wavelengths that plants can't use and then re-emit wavelengths that plants can use. That's the concept. So they're absorbing ultraviolet light, some blue light and green light, and then they're emitting very strongly in red wavelengths, which plants can use for their growth. Another innovation on the technological side is that we're going to be using an optimized control system to try and maximize plant growth and electricity production. And then finally, on the right-hand side there, you see that we're going to be using the panels to both collect water in order to use for irrigation, but then also to protect crops from heavy rain and from hail. So we're ready with our simulation and test platform for the nanomaterials. So we have methods for producing these materials and embedding them in the glass, and then looking at their effects on the spectral composition. And this is the effect of those materials. We've tried two different materials in the nanobeads. So on the left-hand side, these are doped with europium, and on the right-hand side, they're doped with perovskites. And what you're seeing on these graphs, the rainbow colour is the solar spectrum. The very dark, the black curve is the spectrum of light that these materials absorb. The red peaks are the emitted light, and then the dotted lines in the background are the absorbance of leaves. They're the wavelengths that chlorophyll absorbs. And what you can see is that the europium is absorbing ultraviolet and emitting at a short red wavelength, 613 nanometers. The perovskite materials are absorbing over a broader spectrum, and they're emitting at a longer wavelength of 633 nanometers. We've tested these, and we've found that the perovskite ones work better when you put them in sunlight. So we've gone with these. Now, one of the things about the perovskite materials is that we should be able to, through changing the conditions we use in producing them, we should be able to tune the spectrum in terms of the peak width that they emit, but then also in terms of the peak position, so the wavelength that they emit at. So one One thing that we've wanted to do is to understand how the position of that peak influences the crop performance. And so this is work that I've been doing in my group in Sheffield. So we have these controlled environment growth rooms in which we're able to, with a tunable light, it's got multiple LED channels, we're able to produce different light spectra and grow the plants under those and see what they do. And using the tomatoes from Borsa, we've tried enriching the spectrum in 2 different red wavelengths. So a wavelength of 620 nanometers, which is close to the European peak, and 660 nanometers, which is closer to the perovskite peak. Absorbance of leaves in the visible spectrum is relatively unaffected by the growth conditions, but there's some indication that they absorb less in the red wavelengths if they're grown under these red enriched environments. Photosynthesis here. This is a plot of photosynthesis in relation to light for the 3 treatments. The 620 nanometers is kind of orangey colour, and the 660 nanometers is a red colour here. And again, there's a depression of photosynthesis in the red enriched environments. Okay, so this is apparently a bad thing, except that when we look at thermal imaging, so thermal imaging tells us about water loss from the plant canopies. So the cooler the canopies, the more water they're using. So what this is showing is that the red enriched treatments are warmer canopies, which means that they're losing less water. And that's a really good thing in an environment like Turkey, where irrigation water is at a premium, and it's a really strong limitation on crop production water use. So it could well be that this water effect is much more important than the one on carbon gain through photosynthesis. We've noticed that there are no differences in flower number among the different groups. Here's a quantification of that. No differences in the numbers of flowers that are produced. And so our assessment is that, at least the initial work, is that these crops are quite likely to save water underneath the red enriched treatments without significant effect on flower set, at least. And we're pushing it forward to look at fruit production. Okay, so the stage we're at is that the spectral shift has been achieved in our panels, and we're producing these panels at the current moment. Here they are in production. And so you see the blue colour there is the photovoltaic, the solar cells, and they're embedded in this glass that has this nanomaterial that glows red when sunlight hits it and emits red light. And the next stage is to deploy these in the field. So this is the arrangement in the field. We're going to have 4 different plots. So one is our innovation, another is just regular solar panels, and then a control plot with no panels at all, And then we're also going to be having there's another project treatment there as well, so there are 4 in total. This is being installed at the moment in Bursa. So here's a mock-up of what it'll look like under the innovation. So you see the glass, where that would actually be glowing red and emitting red light under sunlight. And the point here is that with the frame, the infrastructure, it's high enough for agricultural machinery to drive underneath and for farmers to do everything they need to do. Okay, and this really goes alongside one of our collaborators at GUNEM have already a pilot installed in the field, which is Turkey's first agri-PV project. You see this is a significant scale covering a large field, and they've been growing crops already underneath this system. Okay, I'd like to thank you for your attention. Follow us on social media, and if you have any questions about the project, please feel free to get in touch with me.